Hello, my name is Brevin Tilmon, and during the summer of 2018, I was a member of the Summer Undergraduate Research at Florida program at the University of Florida. This was a phenomenal experience, and this presentation will explain my research during the program. To begin, I am an engineering physics major at Murray State University, planning on graduating in May 2019. During the summer undergraduate research at Florida, I was a member of the Florida Optics and Computational Sensor Lab led by my advisor, Dr. Sanjeev Kopal, who is on the right in the picture shown, and my PhD student mentor, Christopher Henderson, who is on the left in the picture shown. I am in the middle. Dr. Kopal and Christopher were an immense help throughout my project, and I'm grateful for the skills I acquired from them. Let's move on to the research. When light hits an object, some light rays are reflected and some light rays are reflected within the object before being reflected back out of the object. The amount of light that is absorbed or reflected in an object depends on both the material and color of the object. Aluminum cans and white paper are excellent examples of materials that reflect most of the light rays that hit them. This light ray that is reflected by an object is known as the direct light component. On the contrary, some objects are more prone to absorb light and reflect the light within themselves before reflecting the light back out. Objects like this include non-reflective dark-colored objects and glass. You can see that in this glass cup, light is being reflected many times before exiting the object. The light that is reflected within an object and then out of the object is known as the global light component. My project involves extracting the direct and global component out of an object being illuminated by a light source. Now that some terminology has been discussed, let's move on to the experiments. Traditionally, to be able to measure the global and direct component in a scene, a projector is used to illuminate the scene in a very specific way such that it creates lines that shift up and down on the scene. This shifting of illuminated lines is so that every point in the scene can be illuminated once and dark once, which is crucial for separating direct and global components. The light rays reflect off of the scene back to the camera shown. The first step of my project involves replacing this projector with a MEMS mirror and white light source. MEMS stands for Micro Electromechanical System. For my project, I use a MEMS mirror as shown, and the red circle is the mirror itself. I used software to electrically control the tilt of this mirror to replicate the accuracy of a projector illuminating a scene. Now observe the MEMS mirror and white light source. The white light traveled through a fiber optic cable and was focused through a collimator and aperture before hitting the MEMS mirror. Observe the yellow arrow leaving the light source. This light is then reflected off the MEMS mirror toward the scene, simulating a projector. Let's look at this in a simpler way. Observe the blue cylinder representing the white light source in MEMS mirror. Light leaves the blue cylinder and is reflected in a controlled way by the MEMS mirror. Now, let's look at the entire experiment setup. You can see the MEMS mirror and light source and camera recording the scene. For my experiment, I opted for a folded crease of paper for the scene as the direct component and global component separation are more apparent in creases. Observe the white arrow leaving the light source, then reflecting off the mirror, illuminating the scene, then reflecting to the camera. This dot is moved around the scene in a controlled way to thereby scan the scene. For demonstration purposes, I will show the scanning first with the lights on. Observe the reflected dot starting at the bottom of the scene and scanning to the top of the folded paper. Once the dot reaches the top, it has completed one scan of the scene and moves back to the bottom to repeat another scan. The scanning you just observed is much slower than the actual experiment scene. I will now show you the actual speed at which the MEMS mirror reflects the light for experiment. The scene is still a folded piece of paper, it's just the lights are off. Notice it is hard to see the dot. In order to see the dot in an image, we need a high-speed camera. The high-speed camera has the following field of view when it takes pictures. What I mean by field of view is this is the size of the image that the camera can save. The high-speed camera takes 10,000 images every second, and it records these images at a 1024 by 1024 resolution. Due to these high specifications of the camera, the reflected dot can be seen in an individual image. Recall how when the dot moves from the bottom of the scene to the top of the scene, one scan has been completed. I will now show the combination of the images from one complete scan of the scene. The image is gray because this makes the computation of the image's magnitude simpler. The bright dot in the middle of the folded paper is a reflection of the MEMS mirror and does not move throughout the scanning. It is vaguely visible how in each row of the scan there is a dot. That is because this is a combination of a bunch of dots into one scan. Recall the explanation of a projector creating pairs of shifted lines to make every pixel in a scene dark ones and lit ones. This is achieved by my method in the following way. I digitally create these scan patterns based on scans within the combined scan. Observe from picture 1 to 6 how the lines are shifted upwards. Now that these shifted lines are created, the separation algorithm can be implemented. So, the combined frames for one scan are shown here as you have seen. This is then broken down into shifted pairs of lines. These shifted pairs of lines are then passed through a separation algorithm that creates an image showing the direct component in the scene, the regular combined image in the beginning, and the global component image in the scene. The direct, global, and regular images can be seen here. Recall that the direct component is the combination of the reflected light in a scene. Since we had a white background and light paper, almost all light was reflected, which is why the direct component image is bright. Compare this to the global image. Recall the global image is the combination of the absorbed light in a scene. Due to having a white background and light paper, almost no light was absorbed in this scene, hence the global image is extremely dark. Now notice the crease in the paper in all three images. As mentioned earlier, this crease accentuates the separation. You can see in the direct image, the crease is bright. In the regular image, it is not as bright, and in the global, it is very dark. Separating global and direct components from images of shifted pairs of lines has been achieved using the MEMS mirror and algorithm presented in this presentation. Next, a novel algorithm and methodology for separating light components was also achieved. In the separation images previously shown, the shifted pairs of lines were created from a single scan of the MEMS. This video was created by saving 30 scans of the MEMS, hence creating 30 pairs of shifted lines. Each of these pairs were passed through a separation algorithm that outputs a video showing how the separation changes over time. In my experiment setup for the video, I used the same folded piece of paper, but flattened it at first. I then slowly creased the paper so that each scan of the MEMS would capture the separation becoming more apparent with each scan. Shown is the result from the direct light separation using the algorithm developed. Notice how the crease accentuates the separation as the paper becomes more folded. Now observe the global light separation video. The crease in the paper becomes darker over time due to less and less light being absorbed in that area. Next, finally observe the regular video and how it changes over time. Here are all three separation videos side by side. To conclude, I would like to thank Mike Nazareth and Julissa Nunez for making me feel welcome at the University of Florida during the Summer Undergraduate Research at Florida program. Next, I would like to thank Dr. Sanjeev Kopal for providing the opportunity to work on this project. Finally, I would like to thank members of the Florida Optics and Computational Sensor Lab, Christopher Henderson, Xiaomeng Liu, and Zed Tasnim, as each of them helped me throughout my project. Thank you.